Hello again, welcome back to ptet.chemistry channel. So this is a continuation of the topical MCQ on stats of matter. So it's actually topic 4 under the Cambridge International Curriculum. Anyway, so this is quite a straightforward question. They are saying that the ideal gas equation works on PV equal to nRT. So you know the N stands for number of moles, so you can work out M over MR times RT. So if you work out MR, it's going to give you MRT over PV. In fact, this question has got nothing to do with calculation at all. It is basically very straightforward. I'm just rearranging this for your interest, okay? In case you didn't know that. There will be questions that require this rearrangement at some point, yeah? But it's saying that the most accurate value of MR, okay? So ideal gas equation has a series of assumptions, okay? The most important assumption in the ideal gas equation is that you have negligible intermolecular forces. All right, so the most accurate value of MR is when you have the best adherence to the assumption, which is negligible intermolecular forces. How can you get the forces between the molecules to be negligible, to be almost zero? When so far apart. When the molecules are so far apart, then you can get as negligible as possible. How can you get them to be so far apart? When they have enough energy to move very far apart, that is to do with temperature being directly proportional to kinetic energy, which you might have learned or might not have learned from physics, okay? So the higher the temperature, the higher is your kinetic energy to move further and further and further away. They are so far apart that they have negligible intermolecular forces, all right? In terms of pressure, you want to have low pressure because if you apply pressure, the gas molecules will come closer together compared to if you apply lesser of this pressure on the gas, then there will be less of them per unit area, and therefore you have more negligible intermolecular forces, so you want as low pressure as possible. So the kind of explanations are always asked in theory paper, yeah, in A-levels ideal gas kind of theory. Again, the same idea applies here. The greatest deviation means how far it changes, yeah. So you see how it's supposed to be a straight line because of your Boyle's law. So Boyle's law states that pressure is inversely proportional to volume, such that you can get PV equal to constant. For ideal gas, it should be a constant, like a straight line like that. But for non-ideal gas, it deviates more and more and more. It depends on your intermolecular forces negligibility again, yeah. The greatest deviation will come from least negligible intermolecular force. The stronger your intermolecular force, the least negligible it is. We are looking at things like H bond being a stronger intermolecular force than permanent dipole, than just van der Waals. Okay, so when you have NH3, I talk in my other tutorial videos on structure and bonding. I talk about how you can get hydrogen bonding between ammonia molecules, as you would have learned in your case study of NH3 versus H2O versus HF is in every single pre-university courses in chemistry, especially in A-level chemistry, okay? You will have learned this series of comparison, okay, between the extent of their hydrogen bonding. So you have a hydrogen bonded to a highly electronegative element like fluorine, oxygen, and nitrogen, and you have the lone pair on the electronegative element available to form the hydrogen bond, okay? So if I set up van der Waals, permanent dipole, and hydrogen bond, I have van der Waals, I have hydrogen bond. Hydrogen bond is just a stronger version of permanent dipole, yeah? When you have hydrogen bond, you definitely have permanent dipole. It's just that you are stronger, okay? In terms of ethene, it's a hydrocarbon. We are just talking about van der Waals. Same with CH4, is just van der Waals. Same with N2 is just van der Waals. Very obvious. The hydrogen bond is going to make the ammonia very non-negligible intermolecular force, and therefore it's going to deviate from ideality the most, okay, among the examples there. So here is just a random substance it's combustible, so it can burn in oxygen. It's an electrical insulator, so we can say no free ions or no free electrons in whatever state it is. It melts over a range of temperature, so it's a mixture. This one you have covered in O level. When you have a pure substance, it has a fixed sharp melting point or fixed sharp boiling point. The fact that you melt over a range of temperature tell you it's a mixture, so it cannot be a pure substance like SiO2. Okay, it cannot be brass because brass is a mixture of metals, which contain copper and zinc. Because you still have a mixture of metal, you still have metallic bonding, so you still have the free electrons because of the metallic bonding structure, so you can still conduct electricity. Polyethylene is a component of plastics used in many cheap plastic, okay? So they are not combustible. In fact, it's very difficult to burn polyethylene, and they often give you incomplete combustion, giving off a lot of carbon monoxide, yeah? Very dangerous, not good at all. Turns out that paper, I don't know why this example comes up, but paper is definitely a mixture. It definitely does not conduct electricity, okay? It's combustible, you can burn paper easily, it burns, right? Okay, it melts over a range of temperature because it's a mixture, yeah? You get it from the wood, but it's a mixture of other substances mixed into making your paper, all right? So this is related to the equation that I rearranged before, but whatever it is, it's quite easy to rearrange again. So MR is MRT. I move the MR up there, and above the PV can go down, so there's no need to memorize any of this formula at all. The important thing here really is your conversion. I think this question is asking you on the conversion. The mass is already in gram, so that is all good, because for the mole, the mass has to be in gram because the unit of MR is in gram per mole. The mass for 1 mole of the substance in gram, so therefore this has to be in gram to cancel them out, yeah? The unit of R is already given in the data booklet, so that is fine. There's 8.31. Okay, so there's 8.31 in the data booklet. It has a unit, so you can look it up. The temperature here is given in degrees Celsius. You have to convert to Kelvin by adding 270.